All right, let's go. Number 8. Cherenkov radiation, light left behind in a medium. In a vacuum, nothing can move faster than light. That limit, about 299,792 kilometers per second, is built into the structure of space-time itself. But inside matter, light slows down. In water, it moves at only about 75% of its vacuum speed. And that changes everything. When a charged particle, often an electron produced by radioactive decay, passes through water or another transparent medium, it can move faster than light does in that material. Not faster than light in a vacuum, but faster than the local light speed inside the medium. When that happens, the particle outruns its own electromagnetic disturbance. The result is Cherenkov radiation, a faint blue glow often seen in nuclear reactors submerged in cooling pools. It's the optical equivalent of a sonic boom. Just as a supersonic jet compresses sound waves into a shock front, a superluminal particle compresses light waves into a cone of radiation. The geometry is precise. The angle of the light cone depends on the particle's velocity and the refractive index of the medium. The process unfolds in billionths of a second as particles cascade through matter, emitting photons that carry away energy irreversibly. Once produced, those photons scatter, fade, and vanish into thermal noise. It's a small-scale phenomenon, centimeters across, lasting fractions of a microsecond. Yet it demonstrates something remarkable. Under the right conditions, nature allows motion that appears to exceed the speed of light. But this is still a local illusion. The particle is not breaking Einstein's cosmic speed limit. Compared to what comes next, this is only the beginning.
Number 7. Relativistic jets from supermassive black holes. At the center of many galaxies lies a supermassive black hole, millions or even billions of times the mass of the Sun. When gas falls towards these gravitational wells, it forms a rotating accretion disk heated to tens of millions of degrees. Magnetic fields twist and intensify inside this turbulent plasma. Under the right conditions, those magnetic fields channel part of the infalling matter away from the disk and launch it outward along the black hole's rotational axis. The result is a relativistic jet. These narrow beams of plasma can extend hundreds of thousands of light years beyond their host galaxy. Electrons inside the jet spiral through magnetic fields and accelerate to velocities extremely close to the speed of light, often more than 99.9% of it. But when these jets are pointed nearly towards Earth, something strange appears to happen. Because the jet material is moving almost directly at us, while also emitting bursts of radiation along the way, the travel time of successive light signals becomes compressed. To an observer on Earth, knots within the jet can appear to move across the sky faster than light itself. Astronomers call this superluminal motion. No physical object is actually exceeding the speed of light. The effect emerges from geometry, relativistic time delays, and the finite speed of light itself. Still, the illusion is powerful. Radio telescopes have measured apparent speeds of 5, 10, even 20 times the speed of light in distant quasars. These jets evolve over tens of thousands of years, gradually depositing enormous energy into intergalactic space as their particles slow and disperse. Yet even these colossal beams, powered by the most massive black holes in the universe, are still only a trick of perspective. The universe contains phenomena where faster-than-light behavior is not merely apparent from geometry. Something even stranger comes next.
Number 6. The lighthouse sweep of pulsars. When a massive star collapses in a supernova, its core can compress into a neutron star, an object only about 20 kilometers wide, yet containing more mass than the Sun. The density is so extreme that atomic nuclei are crushed together, forming a solid sphere of neutrons rotating in the vacuum of space. Some of these neutron stars spin extraordinarily fast, hundreds of rotations per second. Their magnetic fields, trillions of times stronger than Earth's, channel radiation outward along two narrow beams emerging from the magnetic poles. As the star spins, those beams sweep across space like the beam of a cosmic lighthouse. From Earth, we observe them as pulsars, precise flashes of radio waves, X-rays, or gamma rays, repeating with astonishing regularity. But the outer edge of that sweeping beam can move through space incredibly fast. Imagine a pulsar rotating once every millisecond.
At a distance of thousands of kilometers from the star, the beam sweeps across space so rapidly that the point where the beam intersects distant clouds of gas could move faster than light. In principle, if that beam were projected across a sufficiently distant object, say a nebula several light-years away, the apparent motion of the illuminated spot could cross the surface at superluminal speeds. Nothing physical is traveling that fast. The photons themselves still move at light speed. What's moving faster than light is the pattern of illumination. It's the same geometric effect as a laser pointer sweeping across the moon. Move the pointer quickly enough, and the dot could appear to cross the lunar surface faster than light, because different photons are hitting different locations. Pulsars sustain this behavior for millions of years before gradually slowing as rotational energy drains away through electromagnetic radiation. Yet even these rapidly spinning neutron stars are still bound by Einstein's speed limit. The universe has imagined something far more radical, particles that would only exist beyond the speed of light. And that leads to one of the strangest ideas ever proposed in physics. Number 5. Tachyons, hypothetical particles beyond light speed. Einstein's theory of relativity draws a sharp boundary at the speed of light. Any particle with mass requires infinite energy to reach it. Light itself travels exactly at that limit. But in the equations of relativity, there is a strange loophole. Mathematically, nothing forbids particles that already exist beyond the speed of light, objects that could never slow down enough to cross back into the subliminal world. Physicists call these hypothetical particles tachyons. If tachyons existed, their behavior would be deeply counterintuitive. The faster they moved, the less energy they would carry. Slowing down would require adding energy, pushing them closer to the light barrier they could never reach. In theory, tachyons would always travel faster than light, possibly many times faster, crossing cosmic distances in moments. But their existence would come with troubling consequences. According to relativity, faster-than-light signals could allow information to travel backward in time in some reference frames. Cause and effect could break down. Messages might arrive before they were sent. Even more unsettling, quantum field theories containing tachyons tend to become unstable. Instead of representing real particles, tachyons often signal that a physical system is sitting in an unstable state, like a ball balanced at the top of a hill. In many theories, the appearance of tachyons triggers a process called tachyon condensation, where the unstable configuration collapses into a new, stable state. The transition can occur extremely quickly, sometimes on microscopic timescales shorter than a trillionth of a second. So far, no experiment has ever detected a real tachyon. They remain mathematical possibilities, echoes inside the equations of relativistic physics. Yet even if tachyons never exist in reality, the universe has produced events where space-time itself behaved as though it were expanding far faster than light. Compared to that, hypothetical particles are almost modest. Something far more dramatic happened at the very beginning of time.
Number 4. Gravitational wave ripples from colliding black holes. When two black holes orbit each other, space-time itself begins to move. Each black hole distorts the geometry around it, and as the pair spirals inward, those distortions ripple outward across the universe as gravitational waves, tiny stretching and squeezing motions traveling at the speed of light. For most of their lives, these waves are gentle. Even near the source, space-time bends only slightly. But in the final seconds before merger, everything accelerates. Two black holes, each dozens of times the mass of the Sun, can complete several orbits in a single second. Their velocities climb to more than half the speed of light. The gravitational waves they generate become intensely compressed. And something remarkable happens. The peaks of the wave pattern, the moving interference structures formed as the waves overlap, can sweep through space faster than light. Similar to the sweeping beam of a pulsar, these superluminal patterns arise from geometry rather than motion of matter. No mass travels faster than light. No signal outruns causality. But the structure of space-time distortion can move across distant regions faster than light would cross the same distance. The collision itself releases staggering energy. In 2015, detectors from the Laser Interference Gravitational Wave Observatory measured a merger in which about 3 solar masses were converted directly into gravitational radiation in less than a tenth of a second. During that brief instant, the system radiated more power than all the stars in the observable universe combined. The energy then spread outward across billions of light years, gradually weakening as the wavefront expanded.
Irreversibly, the system settled into a single larger black hole. Yet even this violent reshaping of spacetime remains limited by the structure of relativity. To find something that truly raced beyond light across the entire universe, we must go much further back to a moment when spacetime itself began to expand faster than light everywhere at once.
Number 3, inflation of the early universe. About 13.8 billion years ago, the observable universe emerged from an extremely hot, dense state. But within the first fraction of a second, something extraordinary happened. Space itself began to expand at an almost unimaginable rate. Physicists call this period cosmic inflation. During inflation, the universe may have doubled in size again and again, perhaps every 10 to the 35th seconds. In far less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to something macroscopic. The expansion rate was so extreme that distant regions of space moved apart from each other faster than light. This does not violate relativity because nothing was traveling through space faster than light. Instead, space itself was stretching, carrying galaxies to be away from one another. If 2 points in space are separated by enough distance, the expansion between them can exceed the speed of light. During inflation, that happened everywhere. Tiny quantum fluctuations, microscopic variations in density, were stretched across cosmic scales. Those fluctuations later became the seeds of galaxies, galaxy clusters, and the vast web of cosmic structure we observe today. The inflationary phase ended rapidly as the energy-driving expansion decayed, reheating the universe and filling it with particles and radiation. In a tiny fraction of a second, the stage was set for the next 13.8 billion years of cosmic evolution. But inflation occurred only in the earliest moment of cosmic history. Today, the universe still expands, and across the largest distances we can observe, something even more dramatic is happening. Entire galaxies are being carried away from us faster than light. Compared to that, inflation was only the opening act. Number 2, the expansion of space between distant galaxies. Look deep enough into space and you begin to see the universe as it once was. Light from the most distant galaxies we observe today began its journey more than 13 billion years ago. During that entire time, the universe has continued to expand. This expansion is not an explosion through empty space. It is the stretching of space itself. The relationship between distance and recession speed is described by the Hubble-Lemaitre law. The farther away a galaxy is, the faster it appears to move away from us. At sufficiently large distances, that recession speed exceeds the speed of light. Today, galaxies roughly 14 to 16 billion light-years away are already receding faster than light due to cosmic expansion. Even though their light may still be reaching us now, future light they emit will never catch up to us again. Beyond a certain boundary called the cosmic event horizon, regions of the universe are permanently unreachable. No spacecraft, signal, or beam of light sent today will ever reach them. This process unfolds over billions of years as dark energy gradually accelerates the expansion of space. Entire galaxies drift beyond our observable horizon, fading from view as their light stretches into longer and longer wavelength. Eventually, it redshifts beyond detectability. The loss is irreversible. Once a galaxy crosses that boundary, causal contact is gone forever. Yet even this vast cosmic stretching, where billions of galaxies move apart faster than light, is still governed by the large-scale geometry of space-time. There remains one phenomenon that appears to transcend distance entirely, something that seems to connect particles instantly, no matter how far apart they are in the universe. And it may be the strangest behavior nature has ever revealed. In the microscopic world, particles can become linked in a way that seems to defy distance entirely. This phenomenon is called quantum entanglement. When two particles interact under the right conditions, their quantum states can merge into a single shared description. Afterward, even if the particles separate across vast distances, measuring one instantly determines the state of the other. If one particle is measured with spin up, the other must immediately be spin down. The strange part is that this correlation does not weaken with distance. Experiments on Earth have demonstrated entanglement across hundreds of kilometers using satellites and optical fibers. In principle, the same relationship could persist across light years or even across the observable universe. To Einstein, this seemed impossible. He famously described it as spooky action at a distance.
but decades of increasingly precise experiments, most notably tests of Bell's inequalities, have confirmed that entangled particles exhibit correlations that cannot be explained by hidden classical variables. Yet entanglement does not allow faster-than-light communication. No usable signal travels between the particles. The measurement outcomes are fundamentally random until compared later using classical communication limited by the speed of light. Still, the implication is profound. Across spacetime, particles can remain part of a single quantum system long after they have separated. The connection does not transmit energy, it does not move matter, but it reveals that at the deepest level, the universe may not be composed of independent objects at all. Instead, reality may be woven together by invisible quantum relationships that ignore the distances our macroscopic world obeys. At the largest scales we know, from expanding galaxies to the earliest moments of cosmic history, nothing should outrun light. And yet, in these subtle ways, the universe constantly tests the boundary. We live early enough to witness the universe still revealing its deepest secrets.